In this section, I'm going to talk about looking at this idea of percent composition. This helps us to bridge these ideas of moles to grams and allows us to go back and forth within these more complex molecules we might look at. So this is an example where we're looking at a liquid. It has 8.657 grams of this compound and it decomposed into the various elements. We got 5.217 grams of carbon, 0.9620 grams of hydrogen, 2.478 grams of oxygen. The question is then, what is the percent composition of this compound? One of the things we need is the equation by percentage by mass. So we have the total grams in mass, and then we have the mass of each element. This is pretty simple. All we have to do is take our values that were given above. So I have 5.217 grams of carbon out of 8.657 total grams. And that is going to give me approximately 60.26% carbon. We have 0.9620 grams of hydrogen and 2.478 grams of oxygen. If I divide these by these values that we got for the total, and sorry, we need to multiply by 100 to give us a percentage. We would get 11.11% hydrogen and 28.62% oxygen. For this, right, when we add these all together, these percentages up, we should get something really close to 100%. That should make sense. The other thing that we can do with this is if we, for example, have 100 grams of liquid, if we started with 100 grams, right, in the last question, we said, okay, well, we had 8.657 grams. But let's just say if we had 100 grams of liquid, then we would then have the same number as a percentage, right? We'd have 60.26 grams of carbon, 11.11 grams of hydrogen, 28.62 grams of oxygen. That is a different, so we need to be able to go back and forth between these things. If I start with a percentage, I can convert that into a number of grams in 100, or if I have the number of grams, then I can calculate this percentage. So we need to be able to go back and forth between these two ideas of percent compound, and then if we for example have a percentage, then we can just make up, okay, well, then we're going to start with 100 grams of that compound, and that allows us to use this in these equations to solve more complex problems. That I'll go talk about more here coming up. This next example, I would like you to try this on your own. I just gave you an example. If you're not sure how to do this, go back and look at that last example. It's the same idea. It actually just has less things in it. And the only other trick that you might need to identify is that I only give you the amount of nitrogen and the amount of oxygen that it broke down. And remember that composition of mass has to be maintained. And so if you add both the nitrogen and oxygen together, that's going to be your total. So that's the total starting point compound. And then create a percentage, and then that is all we want to do. So post this in the Blackboard space, and then we'll move to the next question. One of the reasons we might want to determine the percent composition is that it can help to identify a certain type of compound. For example, if we have dinitrogen monoxide, it'll give us that 66% versus 33% nitrogen to oxygen ratio versus 50-50 in nitrogen to oxygen for nitrogen monoxide. So this gives us an idea on how to start to identify different chemical compounds. This works with simple compounds like nitrogen and oxygen. We're going to start looking at more complex compounds that involve carbon, hydrogen, and oxygen, for example, that there are a lot more possibilities for how these can combine with each other. Before we start to get into some of these ideas of composition, percent composition, we have to define two different terms here. One is the empirical formula, and that's the simplest ratio of atoms. So, for example, if we have a sugar molecule that's shown on the bottom right here, we have a certain ratio of carbon, and you may not know this, but this is drawn in a way that the carbons are not shown. There's carbon at each of these corners, and there's a carbon here. So the molecular formula, so if we account for the 1, 2, 3, 4, 5, 6 carbons, we have 6. And then if you'd count all the hydrogens out, there would be 12. And then there are 6 oxygens as well in this sugar molecule. This is the molecular formula. So it is the exact composition of a molecule. Versus the empirical formula that's shown above. Here we divide all of these by 6. So if we divide 6 carbons by 6, we get 1 carbon. 12 by 6, we get 2. Oxygen by 6, we get 1. This is the ratio that's going to show up if we determine the percent composition. So the empirical formula is the most simple formula. The molecular formula is actually the exact actual formula. And if you were to determine the percent mass, and you can go ahead and do this on your own, but I will tell you that regardless of if you use 1 carbon, 2 hydrogens, 1 oxygen, you'll get a ratio of 40% carbon, about 7% hydrogen, and about 53% oxygen from either of these. So it doesn't matter how you do this calculation, the percent mass will be the same between empirical and molecular formulas. But it's important to recognize when you're saying something is the empirical formula, that's not what the actual compound might be. There may be additional studies that need to happen before you know exactly what you have. Now that we have this idea of percent composition and empirical formulas, we want to start to be able to use things in order to determine the empirical formula. And then we're going to continue to build even on this idea to solve even more problems. This is something that's probably worth memorizing. It is going to help us determine the empirical formula. And one of the things we want to do is, this is the saying, it's percent to mass, mass to mole, divide by small and multiply till whole. So it's a little rhyme that will hopefully help you to determine the empirical formula. And this rhyme, I am going to kind of show you how this rhyme works and how we use this rhyme. Here's an example where a compound consists of 72.2% magnesium, 27.8% nitrogen by mass. What is the empirical formula? So the idea of percent to mass, that was the first part of that rhyme, percent to mass. We're going to go back to the idea of assuming that you have a 100 gram sample, because then you can really easily determine that you basically just use those percentage values and change those from percent to mass, right? So that's what this whole thing says, percent to mass. You just change the 72% to 72.2 grams. You change the 27.8% to 27.8 grams. So that's the idea there. That's the first step of the rhyme, percent to mass. The next one's mass to moles. So we need to change the mass to moles by determining the molecular weight. When we have 72.2 grams of magnesium, we want to then change this from mass, which is grams, to moles. So we need to look at the atomic mass of magnesium. And if I have a periodic table handy, I know that 1 mole is equal to 24.3 grams of magnesium. And I also know that if I have 27.8 grams of nitrogen. If I have 1 mole of nitrogen, that is equal to 14 grams of nitrogen. So the grams of nitrogen can cancel out, the magnesium can cancel out. I can determine the number of moles next. When I do that, I get a 2.99 and 1.99 rounded answers. And so that is the mass to moles. So I know this is the number of moles of magnesium, moles of nitrogen. The next step is to divide by small. Sorry, this is overlapping here a little bit. Now this means I'm going to divide both of these by the smallest number, that the number of moles that I have. That's going to be, in this case, 1.99. And what this is going to do is give me, hopefully, whole numbers. So if I take 2.99 and divide by 1.99, I will get 1.5. And then for 1.99 divided by 1.99, I would get 1. The next step states multiply till whole. And that means I multiply these numbers that I've generated from step 3 until I can get a whole number. And usually you're going to you multiply by the lowest number you can. So if I multiply by 1, obviously they just stay the same. If I multiply by 2, then you can, maybe sometimes it's helpful to start a chart and you can just kind of keep going until your numbers end up being whole numbers. So if I multiply by 2 here, I'll get a 3 and I'll get a 2. You can multiply by 3 as well, but then you'll get a 4.5, right? So you have the same problem where that won't really work. So this, if we just multiply by 2 here, then those values are a 3 and a 2. Those numbers then tell us how many atoms are in that molecular or that empirical formula. So for this, we have magnesium and we have nitrogen. The magnesium, that number is a 3, and the nitrogen, that number will be a 2. So this is our empirical formula for our magnesium nitrate compound that we are talking about in this question. Okay, I want to work through another example. And in this one, we have a number of grams of a compound that was analyzed, total number, and it contained a certain number of grams of carbon. We have a certain number of grams of hydrogen, nitrogen. So calculate the empirical formula. Again, we'll remember the percent to mass, mass to moles, divide by small, and multiply until whole. We first need to determine the percent mass. So we don't have this yet. And in order to do that, we need to get the percent first, because if we just start taking grams of these compounds, then we're not going, and we go right to moles, we're not going to have the relevant ratio of those. So we need to actually determine the percent mass first. And this is a little tricky because you might think, oh, I can just go to moles and then figure it out that way. But you actually have to start with the percent mass. So in order to do that, again, we'll go to the number of grams of carbon and divide that by the total number of grams in the sample. We'll do that with nitrogen as well and hydrogen. So this is the hydrogen, divide it by the total, and then finally the number of grams of nitrogen. Apply those ratios by 100 to get a percentage and do those calculations. So then we get 38.67% carbon, about 16% hydrogen, and approximately 45% nitrogen. So now we have the percent. We need to change the percent to mass. And again, all we do is change the percentage sign to grams. Now we need to just check when we add all of these together, the 38 plus the 16 plus the 45, we need to make sure that that equals approximately 100. And so this does, when we add all of those up, it's close to 100. So we know that percentage is 100%. That tells us that we're on the right track here. And then we can, only if those percentages add up to 100, then you can move to determine that, okay, this percentage is the same as grams in this instance. So we're going to change this to grams. And we'll move on to that next question where now we change the mass in grams to moles. So I'm going to move to another clean slide here. And then we're going to need to know the atomic weight of those. Carbon is 12 grams of carbon per 1 mole carbon. Hydrogen is 1 gram of hydrogen per 1 mole of hydrogen. And then nitrogen is going to be 14. So if we take 38 divided by 12, that gives us approximately 3.16. 16 divided by 1 is going to still be 16. And then we have 45 divided by 14. That's going to give us 3.2. So remember, it's percent to mass, mass to moles, that's where we are now, divide by small, and then multiply until whole. So the small number here is the 3.16, and that's going to make carbon 1. If we take 16 divided by 3.16, we will get approximately 5, and then 3.2 divided by 3.16 will be really close to 1. We're not always going to get exact, precise numbers. You kind of have to use some kind of estimation or guessing that this is going to be correct. If there shouldn't be an example where it's going to be too many decimal points off. So for example, if I do divide 3.2 divided by 3.16, I get 1.0126. So that's telling me that's really close to 1. And remember, there's always going to be error in these calculations. There's going to be errors in how much stuff how you're doing your measurements. So this is really close to these values. This gives me some idea that this is probably pretty close to my empirical formula, and then I don't have to multiply until whole. This was close enough. I can do some really close rounding. Now if you're at like 1.3 or 1.25, then you might want to consider, okay, so that's a pretty big difference, and that rounding is quite substantial. Then you would want to consider multiplying until whole. So, but in this case, we can be pretty confident our empirical formula is C1H5N1. This is a classic example of how empirical formulas were determined. And usually what you're doing is you're taking your compound that's going to be analyzed, you would burn it, you'd ignite it, and you'd send it through these various compounds that would then absorb water, for example, and absorb carbon dioxide. And when the water is being absorbed, then we recognize and we're adding here an oxygen source. So oxygen is used to burn and heat, and then the water is going to be made up of anything that any hydrogen in here, and also the oxygen that's being added. And the carbon dioxide is going to be from the oxygen and carbon that is being absorbed here, and then the oxygen leaves. So usually if we know that these can be changed into other compounds whose formula is known and the weight of those is known, and then we can kind of work backwards to determine that. A more modern analysis will actually do something similar where we have our sample and you're going to kind of do the same thing. You'll burn it, and then it goes through an injector and a column and a detector to tell you basically how much is there. So these can be burned completely in pure oxygen, and then we get something like the combustion of methanol. It'll give us various peaks, and these can even look at sulfur content, nitrogen content. It'll look at more things than just carbon and oxygen and hydrogen. Here's kind of a write-up of what I just talked to you about. in terms of the analysis. So when you look at carbon dioxide, you'll notice that there's one carbon in every molecule of carbon dioxide. So when we're doing that analysis and we identify carbon dioxide, 1 mole of carbon dioxide is equivalent to 1 mole of carbon. All of hydrogen ends up as water, and for every 2 moles of hydrogen, there's 1 mole of water that's made. And then if we know the compound only contains carbon, oxygen, and hydrogen, the mass of the oxygen is actually determined by subtracting the mass of the sample minus the mass of the carbon and hydrogen combined. And again, that's because we're actually pumping in excess oxygen to allow for combustion. So you can't use the kind of same carbon dioxide or oxygen or water above in order to determine the oxygen concentration. Here's an example of combustion analysis in this kind of compound. And we're looking at combusting a sample that's 5.217 grams, and it contains carbon, hydrogen, and oxygen. And we're using pure oxygen to burn the sample. And we get 7.406 grams of carbon dioxide, 0.4512 grams of water. So now we want to calculate the empirical formula for this compound. Remember, all the carbon ends up as CO2, all of the hydrogen ends up as water, and then the mass of the oxygen's obtained by the difference there. So to calculate the mass of carbon from the mass of CO2, this is our steps. We're going to go from mass of carbon dioxide to moles of carbon dioxide. We're going to use this ratio of a 1-to-1 ratio of moles, that conversion factor, to give us carbon and then turn it into the mass. So we will take our 7.406 grams of CO2 that were given above, and we're going to use the molecular mass of carbon dioxide to convert the grams of CO2 to moles. Now we have moles of CO2. Now our next step is to get moles of carbon. I mentioned before that conversion factor is a 1-to-1 ratio. 1 mole of CO2 will give us 1 mole of carbon in that combustion reaction. So now we're at moles of carbon. All of our units have canceled out. And now we need mass of carbon. And now I'm going to use the atomic mass of carbon in order to do this next step. 12.011 grams of carbon is equivalent to 1 mole of carbon. Those units cancel. And then I have my number of grams of carbon, which when calculated should come up to be around 2 grams of carbon. We'll next do this with hydrogen. So this is carbon. Now we want to do this with hydrogen, the same thing. We start now with, instead of CO2, we do the H2O. We get moles of H2O, moles of hydrogen, and mass of hydrogen. This conversion is a little different for hydrogen, and we'll get there in a second. So let's start with the 4.512 grams of water. We're going to use the molecular mass of water, which is approximately 18 grams of water per moles of water. This conversion factor is a little different because there are 2 hydrogens in every 1 water molecule. So if I have 1 mole of water, I actually get out 2 moles of hydrogen. And then I want to convert the moles of hydrogen to grams of hydrogen. 1 mole of hydrogen is equivalent to 1.008 grams of hydrogen, as shown in this part of this chart that I have shown you. And then when we multiply all of this through, we should get 0.5049 grams of hydrogen. Adding these together So I'll get about 2.5. But we know the total is 5.217 grams total. And if I subtract the 2.021 grams of carbon and subtract the 0.5049 grams of hydrogen, I will get 2.691 grams of oxygen. So that is how we set up that first part to determine the mass. So this is the indirect analysis. So now we get percent to mass, mass to moles, divide by small and multiply till whole. So then we would make these percentages, and then we could determine the empirical formula from here. So here we are at this grams. I've just kind of calculated these the same way that I just showed you on that previous slide, put them in this chart. And now the next step is to determine the percent to mass. In order to determine the percent composition, remember I take that value I calculated, the 2.021 grams of carbon, divided by the total grams, so that was 5.217 multiplied by 100. I do the same with hydrogen, and with oxygen, divide it by the total to get my percentage. This gives me percentages of about 38. These, if I add those up, are going to be approximately 100%, which is good. Then I can generate those back into grams that would be associated with a 100-gram sample. And this, I would have 38.74 grams, 9.68 grams, 51.58 grams. We can convert those back into the number of moles using the atomic mass. Then I'm able to get approximately 3.23 moles of carbon. Sorry, that got cut off. 9.6 moles of hydrogen, 3.24 moles of oxygen. Here we go from percent to mass and mass to moles. Divide by small. So we're in moles here. I'm going to divide by the small value, which is the 3.23. And I get approximately approximately 1 down here. And the 9.63 is at 2.97. So we can estimate that's a pretty close to 3%. So I'm going to bump that up to 3. So we're going to C1H3O1. So this would be a reasonable guess for an empirical formula for this compound based off of that combustion analysis example. Okay, it's your turn to follow those same steps. We're going to combust 13 grams of a sample, generate 19 grams of CO2, 11 grams of water, and you'll just follow those same processes and steps. So you might have to go back and look at those. You're also going to have to determine yourself the atomic weight of carbon, hydrogen, and the molecular weight, or sometimes referred to as molecular mass, for water and carbon dioxide. Your answers should be one of the following, so this should give you an idea, but it's a long process, right? We have to go determine the percent composition, then we can turn that percent to mass, mass to moles, divide by small and multiply it till whole, and then we should get this empirical, one of these should be your empirical formula. So post your answers, and then we'll determine if you have any questions, we can work through those